Hello everyone, and welcome to day 2 of our honors topic about patterns. Now, a little follow-up from what we did yesterday. Remember we made the Fibonacci spiral, right? Remember making that? So I decided to, because, you know, I'm me, and that's what I like to do, I actually did some parabolic curves in the Fibonacci spiral, so I'm putting all sorts of things together, which I think turns out to be pretty cool. And then on top of that, I'm not finished yet, but I did some parabolic spirals in the Fibonacci swirl as well, or in the boxes. And it's just turning out pretty cool. So anyway, you can take this stuff and make of it what you'd like. There's so many things that you can do, that I can do, that we can do. Alrighty, so we're gonna start with Pascal's triangle today, and Fibonacci is totally related to this, so that's cool. You need to use this kind of graph paper. Notice normal graph paper has the squares right on top of each other, right? So the square, and I need something that's offset. So this one looks like bricks because it needs to be offset for how we need Pascal's triangle to be written. So if you use the one that I printed or that is on the page, if you count one from the side that has the long, count 8 over, that'll get you to the middle brick. 1, 2, 3, 4, 5, 6, 7, 8. And put a 1 in that brick. Okay? Now, like if you want to think about it, it's like the rest of the rows are zeros, but you don't have to worry about that. Okay? Now, just to get this started, we're going to put a 1 in the next one down, both on the diagonal like that. Okay, now from here on in, the number that you get is the sum of the boxes above it. Okay, so this box has a 0 because nothing's there, plus a 1, so that's going to stay a 1. This box has a 1 and a 1, so that adds up to 2. And then this box, again, will be a 1. Okay? Then we're just going to keep going. We're going to fill this in, and go ahead. You can go all the way till, okay, I'll talk to you later. All right. This one goes all the way. Just fill it in as much as you want. Take your time. I'll fill this in kind of quickly so that this doesn't take forever. But again, Pascal's triangle, now I only heard of this because there's like one main use that they use for math class, but the more and more I study it, the more I find out there are so many patterns embedded in this situation that it's just crazy powerful. There's so much stuff in here. Okay, 6, 15, 20, 15, 6, 1. Hopefully you're noticing a pattern. 1, 7, 21, 35, 21. Nope, sorry, that's also 35. Then 21. I can do this. 7 and 1. This helps us see. We're going to keep going. At least a little while longer. 1, 8. We'll get down to 10 at least. 28, 56, 70, 56, 28, 8, and 1. And then 1 and 9, 36, 84, 126. Yeah, the numbers are starting to get big. 126. 84, 36, 9, and 1. And last one, 1, 10, 45, 120, 210, 252, 210. These are big numbers. 120, 45, 10, and 1. Okay, now, as you can tell, this pattern can go on forever. And it just keeps going and going. Now, so hopefully you guys can see some patterns that have already emerged. Obviously, the outside lines are ones, okay? And then the next line in are counting numbers, and it can go either way, either this way or this way, okay? And hopefully if you noticed that if we fold it in half, it's symmetrical, so it matches. You know, it's got, yeah, it's symmetrical. Okay, so then if we keep going on the diagonals, so we got the ones, we got the counting numbers, the next row, 1, 3, 6, 10, 15, 21, and so on, those are actually called the triangular numbers. So if you're making a triangle, you can make a triangle out of this many dots or squares of something, or yeah, of things. So if we have 3 dots, we can make a triangle. If we have 6 dots, we can make a triangle. If we have 10 dots, we can make a triangle, and so on. So those are called the triangular numbers. The next row in after that are actually called the tetrahedral numbers, which would be a triangular based, I'll give it to you later, okay? It would be a triangular based pyramid. So again, it's how many points you need to make one of those. We're actually going to talk about tetrahedrons when we do platonic solids on Thursday. So cool. All right, so there's that. And I talked about some symmetry, which is cool. Now, we can also look at the sums of each row. So if we do that, like we add them up, and we get that row adds up to be, hopefully you can see this, sum of that one is 1, the sum of this row is 2, 4, 8, 10 plus 4 is 14, 15, 16, and 32, and 64. Yes, I've done that. Done the math previous to this, okay? But if we add all of those up, it should add up to 64. Now, this set of numbers is actually something as well, and these are the powers of 2. So if we multiply each number by 2, we get to the next one. So this is actually 2 to the 0 power. Any number to the 0 power gives you 1. Anything to the 0 power gives you 1. Okay, 2 to the first power is 2. 2 squared is 4. 2 to the third power is 8, and so on. 2 to the fourth, 2 to the fifth, and 2 to the sixth. Okay, so that's kind of cool. But there's also other powers involved in the triangle. So if we just take these rows across as numbers, so if we take it, so this would be number 1, and then the next row would be 11, and then the next row would be 121, and the next row would be 14,641, and so on and so forth. And if we keep going down, we actually get, oh, except for, oh, I skipped a row. Just kidding. I was like, why did not match my paper? 1, 3, 3, 1. Ha ha ha. And then this one is 1, 4, 6, 4, 1. Woo, I was confused for a second. Okay, so if we just take the rows themselves as numbers, then it turns out that each one is the powers of 11. So this is 11 to the 0 power. This one is 11 to the first power. This was 11 squared. This one's 11 to the third, 11 to the fourth, and so on. And there's a way to deal with the double digits within there. I just can't remember what it is right now. But it's definitely, is if you handle it that way, it still works. Let me see. Oh, you just add that double digit into the number that comes. You just carry it. You just carry it. Totally works. Okay? So, there you go. Now, there's just so many. I wanted to get to the Fibonacci sequence because the Fibonacci sequence is totally in here, but there's just so many patterns in this thing. So this one is saying for the second diagonal, so looking down the counting numbers, for the second diagonal, the square of a number is equal to the sum of the numbers next to it and below both of those. So if we squared this number, then that is the same thing as this plus this. So 4 squared is 16, which is 10 plus 6. 5 squared is 25, which is 10 plus 15. 6 squared is 36, 15 plus 21. See, totally works. Isn't that cool? Ooh, there's another one that you could do down any diagonal, and it's called the hockey stick. This one's new, people, or it's new for me. Again, I've tried to learn new stuff every day. So you can do like a hockey stick situation. So you take a stick, and we're going to add each of the numbers up in a diagonal until we decide to come down. So let's say we did 1 to 4 to 10 to 20, and then over to 35. So it kind of makes a hockey stick. If you add these up, it should equal the number at the end of the stick. So 1 plus 4 is 5, plus 10 is 15, plus 20 is 35. Dun, 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 dun. Okay, and that works down any diagonal. So we could do it this way. We could do 1 and 6 and 21. And does that equal 28? Yep, 1 plus 6. We could go one further. Do 1 plus 6 plus 21 plus 56. And does that come out to be 48 or 84? That's 7. That's an 8. And that's a 4. Carry the 1, so that's a 3. And if yep, 84. Okay, so many different patterns in this one triangle. Let's see, next. Okay, so the Fibonacci sequence, because we talked about that yesterday, right? And you don't just look at it automatically and recognize or see the Fibonacci sequence, but it's kind of buried in there. Okay, so make the pattern by going up and then along, then add up the values. And so we can start with 1, and we start with this one, and then we start with this one, and then you're going to go, it's kind of down 1 and over 1. Okay, so we're going to take this one plus this one, which gets us our 2, and then we're going to start with this one and go down 1 over to the 3, down 1 over 1, sorry, down and over 1, and then down and over 1 again. So this one, and this one, it's kind of like in every other one, and that gets us our 5. And then we come to this one, 1 plus 6 plus 5. Oh, I skipped a row. 1 plus 3. Yeah, we did that one. So 1 plus 6 is 7. Plus 5 is 12. Plus 5 is 13. I missed one. Somewhere I missed. Oh, 1 plus 4 plus 3. 1. Oh, this one. 1. Anyway, there is an 8 in there somewhere. If you look, I've got it on my computer. So if you follow the colors right there, focus. Okay, so they're in light green. The 1, 3, 1 is the 5, and then the 3, 4. Oh, because it doesn't start with 1. That's why I was confused. 3, 4, and 1 gets you the 5, and then the 8 and the 13, and so on. Okay, so Fibonacci sequence. Sweet. In Pascal's triangle. It's so cool. Okay, now you can use Pascal's triangle for probability. We won't be using it for probability just because the probability that we do is not quite that technical. But eventually you can totally use it for probability, and that's something that I didn't know about. The only place that I knew about it in math class was for expanding polynomials, and this is something that you wouldn't understand because you haven't done the math yet. But yeah, when you get to expanding polynomials, that's really the only thing that our classrooms use Pascal's triangle for, which makes me sad because it's so much more useful than just that, right? Even just in these few minutes, I've shown you lots of different patterns, okay? Lots of different cultures knew about this and use this. It has lots of different names. I'll attach a little video that kind of goes over all of these things as well. And the last thing I want to do with Pascal's triangle is, if we remake it, we're leaving all the ones, well, basically writing down all of the odd numbers, or filling in the triangles with the odd numbers, and leaving, the even ones blank. So again, I'm going to start again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to fill that in because that's an odd number. I'm going to fill this one in and this one in because those are ones, right? I'm not going to fill in 2 because that's even. Then the next row is all odd. I'm just trying to be fast here. Okay, then the next row is odd, and then even, 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 odd. And then the next row is odd, odd, even, even, odd, odd. And if we keep going this way, so the next one, and then 6, and then 15, and then 20, and then 15, and 6, and 1. I'm gonna keep going. And this, and 7, and 21, and 35, and 35, and 20. Those are all odd. Oh, that means I should be coloring them in. Backwards. Okay, and what begins to emerge is what's called Serpinski's triangle. Okay, and it sounds like somebody might have already talked about Serpinski's triangle in one of the previous classes, and that's totally cool, but you can get it out of Pascal's triangle, which has all the other things as well. So let's see, 1, 8, 28, 56, 70, 50, those are all even, except the last ones. Okay, so we're actually going to make Serpinski's triangle on the other side of this paper. I have given you, or on for you guys at home, you just have to print out both papers, okay? So I've made an equilateral triangle, meaning all 3 sides should be the same length, and they should all be 8 inches. So what I want you to do is find the halfway point for each of the sides. So we start off at 8 inches, so the half is at 4, and find that on all 3 sides. Okay, so we're going to mark 4 inches on all 3 sides. And then we're just going to connect those. We're going to connect those dots to make a triangle inside the triangle. And it should be going the opposite direction. Okay, the more accurate you are, the better it's going to look. You know me, I love drawing straight lines. It's my jam. Love drawing stuff with rulers. Okay, so now all of a sudden we have 4 triangles. Now, each of the triangles that's pointing up, we're going to do the same thing again. So we're going to leave the center section empty. But now each of these sides should be 4 inches, which means if we cut that in half again, we measure 2 on each of these sides. And again, the more accurate you can be, the better it's going to look. And yes, this is going to take a while, but that's okay. Okay. Making triangles, making triangles. Okay. Triangles. All right, and you can see that if we do that in all 3 of those, it starts to look the same. And then we can do it, we can just keep going. So these smaller triangles should be 2 inches, so half of that is 1 inch. And you can do this again in all of the upward facing triangles. and it will fill in Serpinski's triangle. So I would like you to do at least 4 iterations all the way around, meaning follow this pattern and fill it in all the way around. Okay, and you can keep going and keep going and keep going. I will attach, well, I'll show you a picture first, and then I will attach a video that kind of shows the fractal nature of this Serpinski's triangle. Okay, and that will lead us into fractals, which is what we're going to be talking about tomorrow. Okay, so let's see. I was going to show you a picture first of all, but then I have to find it. There it is. Okay, Serpinski's triangle. Okay, and apparently you can use any shape if you want to, but again, it's a fractal. So start with a triangle, and then more and more. They colored them in, and you can just keep going and keep going. So I'll attach a little video that talks about Pascal's triangle, and it covers pretty much everything that I went over, and then another little video that covers, so you can just see the fractal nature of the Serpinski's triangle, because it's pretty cool. Okay, and then finish filling in as much of Serpinski's triangle as you can, and try to make your Serpinski's triangle, fill it in at least, go at least one more small and do it over the whole thing. You can do it. It's fun. It's smart. Okay? Have a great day. Bye.